Okay, so so remember what we're doing, right? The last time we got the solution to the wave equation, right? We got the solution to the wave equation. Wave equation in R d plus R, right? And it was this long, complicated thing, right? It was like u of x t equals, the inverse Fourier transform the inverse Fourier transform of this sum f hat c cosine 2 pi absolute value of c t plus g hat c sine 2 pi absolute value of c t over 2 pi absolute value of c, and we take the inverse Fourier transform of it 2 pi x dot c. Right. So we have this long thing, and whoops, and this turned out to be a solution, but it's kind of an unsatisfying solution in some sense, right? Like if you try to think of it, what does it tell you about the solution in terms of f and g? It is a solution, but it doesn't really. It's kind of a not really illuminating solution, right? And so what we're going to do today is basically give more physical interpretations. Okay, so that'll be nice. And the inspiration, right, or the sort of like prototype of this sort of solution is D'Alembert's solution. So way back in the first chapter, we did D'Alembert's solution to the wave equation in R1, and it turned out to be u of xt equals f of plus t plus f of x minus t over 2 plus 1/2 the integral from x minus t to x plus t of g, right? And that was D'Alembert's solution, right? So I'm just saying that last time we got this kind of in almost like opaque description of the wave equation solution, and this time we're going to do a more like physically illuminating one that whose prototype is basically D'Alembert's solution, because D'Alembert's solution says that what this is going to be an average of the function, right? So you take the at x, right? At x, you take x plus t, x minus t, and you average them, right? And similarly, you take from x minus t to x plus t, you take f at the edges of that interval, and you average it there, and you also take the average. Well, this doesn't look like it. If we make it look more like an average by dividing by 2t and then multiplying by that t, right? So now this is t times the average of g over that interval, right? So that's D'Alembert's solution, and we're basically going to do a bunch of calculations today that will turn this thing into something that looks more like this thing. Okay, so it'll look more like averages of the function. Okay, so yeah. Okay, so we start off with something called the spherical mean. So definition, we have some function. So we'll first do the R3 case, and then we'll do the R2 case, and we'll see that those two are kind of distinctly different. Okay. So first, start off with a function on R3, And we define the spherical mean, so mt of f at x, right, is going to be average of the sphere of radius t. So average over the sphere of radius t, centered at x. Okay, and that turns out to be this thing here. So f of x minus t gamma, d sigma of gamma, integrated over the sphere, divided by 4 pi. And remember that this was basically an abbreviation for the, this is basically an abbreviation for this. The integral, using spherical coordinates. So this is f of x minus t gamma, sine of theta, d theta, d phi, as theta, where gamma is sine phi cosine, sine theta cosine phi, sine theta sine phi cosine theta. Yeah. Okay. So this thing here was basically an abbreviation for this. Okay. Okay. And so right. So this is what they call the spherical mean. Okay. So spherical mean. Okay. And what we're going to get in the end is the following. We'll see that that this thing that we have here, the solution that we have that we worked out last time, can be reinterpreted as the following. So we'll show that u of xt actually is the partial with respect to t of t times the spherical mean plus t times this plus t times the spherical mean of g. Okay, so that's the goal. To see that that this thing can be expressed in terms of means of the initial data. Okay. Okay, so like pictorially, if we think of this thing as RD and this is R, so pretending that this is d-dimensional space and this is R, right? So x lies in here, t lies in here, right? If you're at some point xt, then what it says is that if you look at the initial data at the point t, so remember the initial data is on RD at time 0, right? Then if you take the spherical mean of f of radius t, so this is height t, so if you make a radius of t here, right? It says that that the value that the wave the value of the wave at this point depends entirely on the initial data in a small neighborhood of this sphere here. Okay. Right. Does that make sense? Right. right? So right, you're taking the derivative of this the spherical mean here, right, which is going to occur over here, right? So right, this value here is determined entirely by the values in a small neighborhood here, in an infinitesimally small neighborhood of that sphere. Okay. Okay, so that's the goal, and the proof of it is not too hard. It's basically a lot of calculations. So let's do it. So there's a bunch of lemmas that we're going to need. First, that for f in the Schwartz class, then for each t, mtf is still in the Schwartz class. Right? You're taking average of the functions over the averages over the function over spheres. And that's still going to be satisfy the decay and smoothness. Further, MTF is infinitely differentiable in T, and all derivatives are still in the Schwartz class. The second lemma we're going to need is that if you take it's just a calculation, 1 over 4 pi. If you take e to the negative 2 pi I c dot gamma, and you integrate that over the sphere, then what you get is sine of 2 pi absolute value of c over 2 pi absolute value of c. Okay, so that should look kind of suggestive, right? It looks a lot like the term, the term that g hat is multiplied by in the solution. Okay. And then the third one, the third thing we're going to need is that the Fourier transform of the spherical mean actually turns into the product of f hat against sine of 2 pi absolute value of c over 2 pi absolute value of c. Okay, so regarding these last two, so remember the spherical mean looks like this, right? 1 over 4 pi integral over s squared f of x minus t gamma d sigma gamma d sigma of gamma, right? One way of thinking about this is that it's a convolution of, it looks like a convolution, right? This is actually what's called a convolution of a function against a measure. Like f convolved with the measure. Okay, and so this thing here, what's this? Well, this is the Fourier transform. You can think of this as the Fourier transform of the measure, right? You're integrating the measure against e to the negative 2 pi I, blah. So this is the Fourier. This is in reality the Fourier transform of d sigma, right? And what this last thing is saying is that when you take the Fourier transform of the convolution, you get the product of the Fourier transforms, right? So you get f hat against the Fourier transform. You get f hat against d sigma hat. Okay, so that's what's going on here. Okay. So yeah.
Is this analogous to you take Fourier series over the circle? Is there something here over the sphere and so on and so forth?
I'm sorry, say one more time.
Fourier series, instead of considering the function over all of R, you consider the function over the circle. Is there something like that happening here, where instead of considering the function over all of R3, you consider the function over the sphere?
Oh, so it's sort of like a polar integral for
yeah.
I think that's right, but I think it's something like that. Give me 1 second and let me think. And yes, I think that's right. Yes. Yeah. Okay. Okay. Sorry. Let me. Okay. So. So once we have these lemmas, then it's actually pretty straightforward to see that the solution that we got last time, it's pretty easy to get the expression of our solution in terms of the spherical means. So maybe let me just sort of show you how that happens. So. So remark, once one has the lemmas, the goal is easily obtained. The goal is easily obtained, right? Because right, u of xt is this thing, right? This f hat c cosine 2 pi ct. Let me just break it up into two parts. Equal to 2 pi I x dot c plus the other part g hat c sine 2 pi c t over 2 pi c e to the 2 pi I x dot c. Right? But we can write this as we can rewrite this part as the partial with respect to t of f hat c sine 2 pi ct over 2 pi ct. sorry, times t. Right? So we're just playing tricks here, basically, right? We say, look, you know, if we multiply by 1, and we've got a t over t here, you know, this cosine of 2 pi ct is just the derivative of the sine of 2 pi ct over 2 pi c, right? So that's just a calculus trick, right? Right, but then you see that what this is, but this thing then is the inverse Fourier transform. That's the inverse Fourier transform of the Fourier transform of the spherical mean, right? This thing here is the spherical transform, the Fourier transform of the spherical mean, right? And so we're taking the inverse Fourier transform of that, and so you know, this first term just turns into d dt of t times mtf and x. Right, and even more simply, with the second term, you say, well, I'm just going to multiply this thing by t, by t over t. So this is t right. I multiply this thing by t, and that sorry, there should be t's here. That's what's putting you guys off. There should have been t's there. Sorry, back here. Okay, so
Should there be t's in just above that as well?
no. Yeah, there's no t here. This is just the Fourier transform of the. There's no t in the term.
Oh,
Yeah. Yeah. So here, you know, we wanted to look like, you know, we want to look like the inverse Fourier transform of the spherical, or the inverse Fourier transform of this Fourier transform of the spherical mean of G, right? So we multiply by t and divide by t. Now it looks exactly like it, right? Right. This thing is now mg m sub t g hat of c, right? And so we end up with this t times mt g of x, right? So once we have these lemmas, then the translation is immediate. Okay, so all we need to do is get the lemmas. I'm gonna erase this. Is that okay? Okay, so I'm gonna erase this just to sketch out where we are. We wanted to show that the solution that we got last time actually has a physical interpretation in terms of the spherical mean, right? That you know, this sort of impenetrable, you know, expression actually has a physical interpretation, you know, in terms of the spherical mean of the initial data, right, and the initial velocity data, right? And it turns out that if we can get these lemmas, then that interpretation pops out immediately. Okay, so now we just need to show these two things, that the Fourier transform of the measure looks like this, and that the Fourier transform of the convolution actually is the product of the Fourier transforms when we're dealing with measures rather than functions. Okay, so I'm going to let you read the proof of the first one. It's just a technical proof. Oops. Okay, so let's show that this is true. That the Fourier transform of the measure actually looks like this. Okay, and the proof of 2. The way we're going to do it is to first observe that. First, we observe that the left-hand side is radial. Okay, so looking at this thing on the left-hand side, the integral of negative 2 pi I c dot gamma d gamma, d sigma gamma, right? We want to show that it's radial, so what we do is we rotate, let me write this as d sigma hat of, so this is d sigma hat of c, and let's rotate it by some, so let R be a rotation. Let R be rotation, and let's look at d sigma hat of R of c. So we have an R of c here. Okay, and we want to show basically that we can get rid of that R. Okay. But this turns out to be pretty straightforward. Say, well, look, this is the same thing as negative 2 pi I c dot R inverse of gamma d sigma gamma. Right, but all that is that we're integrating this function, but we're rotating the variable. Okay, we're rotating the variable over the sphere. So rotating the variable over the sphere is not going to change the integral, right? We're still integrating over the sphere. It's just that we've rotated it here, right? So this actually immediately see that this you can get rid of the rotation, and that's going to be the same as the original. Okay, so that this thing is radial. Okay, so then so since it's radial. So it suffices to show that the formula is true at a single point for so we're at some c equals 0, 0, 0, 0 rho. For any rho bigger than 0. Okay, so you just do the calculation. That thing on the left, remember, is 1 over 4 pi. The integral from 0 to 2 pi Right, so we let phi go from 0 to 2 pi, we let theta go from 0 to pi of e to the negative 2 pi I xc dot gamma, where remember gamma was that cosine, sine theta cosine phi, cosine theta cosine phi. No, sine theta, sorry. Sine theta sine phi, and then cosine theta. Right, so the left-hand side, this thing here is just this by definition, right? And so we have xc dot gamma is just going to be rho cosine theta. This is rho cosine theta, right? Then this is independent of phi, so we can integrate out the phi, right? And we get 1/2 of integral from 0 to pi of e to the negative 2 pi I rho cosine theta. Oops, I forgot something. There should be a sine theta here. Sine theta d theta. Right. And then anyway, it's not that interesting. You do a change of variable, and then you get 2 pi rho over 2 pi rho. Sine of 2 pi rho over 2 pi rho. So it works out. Okay. So it's just a calculus problem. Okay, so so this just turns out to be a calculation. Is that okay? Okay, and then the second one, we want to show that the Fourier transform of this thing is this product. So let's do that. Fourier transform of the spherical mean, right, is going to be, right. So we take the spherical mean, 1 over 4 pi. F of x minus gamma t, d sigma of gamma, right? And then integrate that against e to the negative 2 pi I x dot c, oops, dx. Right, so that's just a Fourier transform over R3. Okay, we combine these things together and switch the order of integration. You get 1 f of x minus ct e to the negative 2 pi I x dot c dx, and then integrate that over the sphere. So just change the order of integration, and then combine things together. Okay. Okay. Then we do a change of variables. So let y be x minus gamma t. Right. Then this turns into 1 over 4 pi integral over x squared f of y e to the negative 2 pi I x, which is y plus gamma t dot c dy is nil gamma. Then we separate this into e to the negative 2 pi I y dot gamma and e to the negative 2 pi I gamma t dot c. Right. And we pull this term out of this. We pull this term out of the integral, right? And that leaves us with the Fourier transform of f. Right. So you end up with 1 over 4 pi Fourier transform of f. Fourier transform of f at c. And then we've got the integral over s squared of e to the negative 2 pi I t dot gamma c against the gamma dot t c. Right, but we, by the previous, that gives us that's just right. This is just the that's just the Fourier transform of the measure evaluated at t c. Right. So that gives us so this turns into 1 over 4 pi f at c sine of 2 pi absolute value of c t over 2 pi absolute value of percent. Okay, I hope that's clear, and right. So here we just take the definition of the Fourier transform. Here we use Fabini's theorem. We change the order of integration. Right, change the order of integration. We do a change of variables that allows us to see that we can pull out the Fourier transform, and what's left is just the Fourier transform of the measure. And we just calculated the Fourier transform of the measure. Sorry. That's right. Okay. So yeah. So maybe not the most exciting. Thing, but I think the physical interpretation is cool, right? That that you can express the wave in terms of averages of the initial condition, right? And along the lines of the comment, they make this comment that what we said before, that this is time and this is space, right? That the solution at this point, right, depends on the data back here, right? The solution at this point in time depends on the data at time 0 in this at the base of this cone here, right? Right, because you're taking the averages, right? You're taking the averages of the function in the sphere. This is this is RD, so you think of this as a sphere, okay? Right? You're taking averages over the sphere of the initial data, the f and the g, right? And then conversely, what they're saying, what it also implies is that if you have some data at a single point here, then the bits of the solution, the parts of the solution that it plays into, can be found by taking the sort of inverse cone, right? Like it's these points that are affected by this bit of data, right? These points are affected by this bit of data because of this statement here, right? Because of the interpretation in terms of the spherical mean, right? So they call this the forward light cone. Forward light cone. Like if you have a flash of light here, then it propagates in this spherical manner around it. Yeah.
What's telling us how steep the cone is?
I think in the normalization of the wave equation, we assumed that the speed was 1.
I see.
Yeah.
Okay.
So if you didn't do that, then you'd get a different aperture for the cone.
Gotcha.
Yeah. Remember when there was an initial wave equation, and then we normalized it so that all the constants vanished.
Yeah.
That was setting the speed to 1.
I see. And then, but if we unnormalize it, we might stretch out our.
Yeah. Exactly.
Okay.
Yeah.
So should we think of spherical means as convolution against the characteristic function of the sphere?
It's not really the characteristic function of the sphere. It's the because this thing here is the measure. This thing is a measure.
Well, it's like a Dirac delta function on this sphere, kind of, right? Because if you integrate just that measure,
Okay. Yes.
it'll
Yes.
give 1. Right?
Yes. Yes. That's accurate. Okay, let me go on. My gosh, I hope to get through the 2-dimensional case as well today, but I must be moving really slowly. Okay, but no need to rush. Okay, so the 2-dimensional case is actually kind of interesting. So wave equation in R2 cross R. So this is so-called Adamar's method of descent. Okay, so the idea is basically to if this is R2, okay. So suppose you have your right. We've got this. Say this is R2, and then we've got our initial data on R2. Okay. So right, and we're trying to find how the wave changes through time, right? But we've already solved it for R3 against R, right? So what we do is we take our initial data, and then we extend it into R3. Okay, we extend it into R3 by basically making it constant. Okay, so you just take your initial data that's on R2 and say, okay, let's just extend it, in a constant way in R3. Okay, that's not quite good because you want your initial data to be in the Schwartz class, right? So instead of extending it as a constant, you extend it sort of temporarily as a constant, and then you let it drop off. Okay, so you multiply it by what's called a bump function. So a function that you extend it by saying, let's be constant up until a certain point, right? And then drop off smoothly to 0. Okay, so doing that to the function to your initial data, and then you solve it. Using what we just did. Okay, and then that will give you the solution, the R2 solution. Okay, so let me just sort of sketch out what happens. I lost my glasses. I'm old. Thank you. Okay, yeah. Okay, so let's see, what should I, got a couple minutes. Yeah, well, let's just get started. So so here's what's going to happen in the end. So we need to introduce an idea. For function f on R2, we define a weighted average. We define a particular weighted average, MTF at x, MT twiddle f at x. Okay, and that's going to be just the integral over the unit disk against. So it's also going to be a convolution. It's also going to be a sort of convolution. So you take the convolution of the function of your function against so over convolution of the function over your unit disk, shifted to x, and then against this measure. Okay. Okay. So. What's going to happen in the end is that, so in the R2 cross R case, our grand solution is going to turn into the following: d of t mt twiddle of f of x plus t mt twiddle g of x. Okay, so it's going to be exactly the same thing, but this time, it won't be the spherical average of the initial data, but it will be this weighted average of the initial data. Okay, so right, so the situation is a little bit different, right? In the right, if this is our point xt, then the solution, the value of the solution at this point is going to depend on the entire disk here, right? It's going to depend on the entire disk because you're taking the weighted average over this disk. Okay. Right, and conversely, right, if you have data at this point, right, then it doesn't just affect the edge here, but it's actually going to affect everything inside. Okay, so the behavior in 2 dimensions is very different from that in 3. Yes.
When y is 1, isn't our inside this integral when y is 1? Do we have the denominator is 0 and a problem there? Do we need to integrate over the interior, or is there?
Yeah. Yeah, I guess you're integrating over the interior. Yeah, or you're taking the limit as the radius goes to 1.
Because it seems like the weight function is giving arbitrarily large weight to the boundary.
That's
Okay.
true. That's true. But let me check that it actually works out. But it does work out.
Okay.
Yeah. It works out because this actually falls out of the R3 by R case. So it's just it's sort of because the R3 case works out, this is sort of guaranteed to be finite. Yeah, this is just going to be this is what this is literally the it's just like the slice of the R3 case, right? So you extend to R3, you take your initial data, extend to R3, right? So that it's constant, between two points, right? That gives you a solution, and then you slice back down to R2. So you say let the third variable be 0. That will give you a solution, u of x1, x2, x3, t, right? And then to get the solution for your original thing, you just set the 3 to be 0. So you're just on this line again. And so it's going to be finite because the solution in the previous case was finite. Okay, that's it.
Thank you.
See you.